Hola a todos.
Hola.
Or should I say hola a tutum? Okay, not many of you. So thanks for joining. I want to talk to you about software design. And early on in my career, I worked at a company where a manager once said, if a good technical design has been made, the code can be written by developers with the IQ equal to a monkey. So who agrees with this? We have no architects in the room, I see. So, but what if I rephrase that statement to, if a good technical design with good instructions on what to build has been made, the code can be written by an AI. Would you then agree? Also not, okay. Well then, we collectively agreed that AI is not yet outperforming monkeys in writing code, right? So all jokes aside, I think we can probably agree that design is a significant part in software development. So let's talk about making design decisions. My name is Bert Jan Schrijver. I'm a CTO at OpenValue, a consultancy. I'm also in the board of the Netherlands Java user group. We have any people from the Netherlands Java user group here? Just those four red ones here. Well, I'm not really surprised about that. So you can recognize those people by their red shirts. I would advise you to avoid them because they usually get in trouble. So at OpenValue, we regularly organize hackathons. So at those hackathons, we work on hobby projects, sometimes including hardware. And at a hackathon a couple of weeks ago, one of our colleagues worked on writing software for an automatic sewing machine, so a máquina de coser. And it looked kind of like this. He also made me holding a coffee cup, which I found quite funny. But he also made this T-shirt for us for this event. Can you zoom in the camera when I hold it up? There we go. So what do you recognize here? Anyone recognize anything on the shirt? Yes, it's the skyline of Barcelona, right? So I guess this is what you get if you give developers access to hardware. Not necessarily the prettiest shirt ever, but it has a good story, right? So for the next 45 minutes, I'll start by talking about definitions with you. We'll tell a story about flexibility in software. I'll talk about different levels of making choices for generic versus specific design. I'll give you loads of tools to help you decide. I'll talk about the cost of generic solutions, when and why it is a good idea to go for generic. We probably also have some time to talk a little bit about sharing code within larger organizations. And obviously, we'll end with a conclusion. I am on Blue Sky, so you can find me here. Feel free to send me any questions there you have regarding this talk. So who of you is into software development? Anyone does anything with software development? Yes, everyone, right? So probably designing software is also part of your work, you could say. So what is software design? If you would need to explain it to a colleague or to a friend, how would you do this? How would you explain what software design is? When I need a definition, I usually go to the internet, like Wikipedia. And Wikipedia says something like, the activity following requirement specification and before programming. So it's between you know what to build and actually building it. Or it involves problem solving and planning a software solution, both low-level design and high-level design. Or software design is the process of envisioning and defining solutions to one or more sets of problems. But it's 2025, so we should also ask ChatGPT. So ChatGPT says software design is a process of defining the architecture, components, interfaces, and data for a software system to satisfy requirements. It involves making decisions about how software will function, how parts will interact, and how it will be structured in order to achieve a problem, solve a problem, or achieve a goal. So I guess that if we look at all those definitions, we can basically say that design is making decisions and coming up with solutions for problems. But then there's the next question. When is something design and when is something architecture? Well, a follow-up question I like to ask is, does it really matter? They're both about making significant decisions, where significant is about the cost of change. If something is really expensive to change, then it's a significant decision. If something is super easy to change, you don't need to think that long about it because it's easy to revert. So if I would need to just make a distinction between software design and architecture, I would say that design is typically local. So within a class or within a project, architecture is typically on a bit higher level, so on a project level or maybe an organization level. And my point that I'll repeat later on is that you can make choices for generic versus specific solutions on lots of different levels in a project or an organization. The same discussion often plays with requirement. Is this a functional requirement or a non-functional requirement? A good question to ask then is, do we really care? They're both requirements, they're both attributes that the system needs to conform to in order to, well, basically make the business happy. So now that we somewhat know what design is, let's have a look at specific or generic design. So a specific solution or a specific design is tailor-made to use in one single place for one specific problem or one specific scenario. And this solution may not be easily adaptable to other situations, but we don't really care. It's a solution that solves one problem in one place. So as engineers, we love crafting intricate and smart solutions, right? So I knew a colleague who said that he could recognize that a certain colleague wrote a piece of code, because he said to me, I know that Frans wrote this. And I said, so why do you know Frans wrote this? Well, it looks super smart, it does amazing things, it probably is super efficient, but I have no idea what it does. So a generic solution is a flexible, a reusable solution. You can apply it to a wide range of problems or a wide range of scenarios. You can use it in more than one place. And talking about those places, that place can be anywhere, like a class or a component or a service or an application or even a team within an organization. When I'm talking about generic solutions in this talk, I'm talking about shared code. So a generic solution is a solution where you use the code in multiple places. So to talk a bit about that hierarchy of places for solutions, I'd like to show a concept, and this is called hierarchical decomposition. And this is, I'd say, a key architecture tactic where you're basically breaking a system or a problem into smaller parts that are easy to understand. For example, if you would need to explain Google to a colleague, then you could say, well, it's Google, you type something, you get results. But maybe the colleague wants to know a little bit more details about the systems, right? So on the top level, the top block of this stack, you could say this is google.com. On the second level, there's probably an indexer that crawls the internet. There's something that provides the actual search. There's something that shows you ads. We all love this. And there's ranking that determines the order of the search results. So if we then dive one level deeper and we go into the indexer, there's probably a component that explores the internet. There's a component that can spider, so connect to loads of pages. A component that can scrape or parse HTML, etc. And by this zooming in and out, you can reason on the correct level of abstraction with someone. And I think it's a core concept of software architecture. It enables you to reason and solve issues at the right level, but also to talk about systems that are beyond the scale that fit in your head. So Simon Brown's CR4 model is a good example of this. We start with the context diagram, which basically shows which systems does our system interact with. Then there's containers, which is nothing to do with Docker containers, mainly large-scale systems. If we zoom into one, we get components, so the components of one system, and one level deeper, we're in the actual code and classes. So another relevant concept in software design is coupling. We probably all know what coupling is because it hurts us every now and then, right? It's a measure of the interdependence between building blocks of software. And a building block is a generic term for something you use in your design and architecture. So a building block can be a class, a component, a service, an application. And coupling measures how closely connected two components or two building blocks are. So when you change something, and something else that you don't want to change, need to change as well, then you have coupling. So low coupling is often a sign of a well-structured system. It usually contrasts with cohesion. So cohesion is a concept that explains how focused a building block is. how well the functionality in a building block belongs together. And ideally, you have low coupling, which means that it's easy to make changes, and high cohesion. So building blocks that do one thing and do one thing well. There are loads of types of coupling. So, for example, you can have coupling through inheritance. You inherit properties or methods from a superclass. Something changes there, you need to change as well. You can do coupling through messages or events. You send something on a Kafka topic, the message changes, now both sides need to change. Temporal coupling. So component A depends on component B because of something in time needs to happen. Component B cannot do their work until component A has done their work. Coupling via data types. For example, you have, Victor was talking about this morning, you have shared client libraries for your REST APIs. And two projects need to make a change. Now the shared library updates, and the third project needs to update as well. But they don't have any interest in this change. Coupling via data. Maybe, I don't know, component A writes something in a database, and component B reads it, and a new value for the field is added. Now component B needs to change as well. And then loads of other different kinds of coupling, usually on code or API, either on a binary, so you have some kind of dependency, or on a source level. And I think it's important to realize that you should be careful with coupling. So obviously, making reusable stuff and having one class call another class is amazing, but it also brings you, well, a less positive side. So I was recently rereading the book The Unicorn Project by Gene Kim. Has anyone read The Unicorn Project? It's a book about DevOps, basically like a novel that reads quite nice. And in this book, Gene discusses the 5 ideals of DevOps. And the first ideal is locality and simplicity. Basically means that locality is a degree to a team can make a change in one place, as opposed to needing to make change in many places. And locality requires simplicity. So if you want to change something in your system and you only need to change one thing in one place, well, then it's relatively simple to change, right? If you don't have locality, you want to change something, you need to change it in many different places, then usually there's lots of dependencies between this piece of code. There's coupling. So I think it's safe to say that dependencies, either between classes, between components, between services, between applications, maybe even between teams or between organizations, they are, I think, the mother of all slowdowns that you have in software development. So they prohibit you from moving freely. They are handcuffs, basically. But also realize that if you are introducing a generic solution that needs to be used from multiple places, you are introducing coupling. So the key is that every generic solution introduces coupling. If you have a piece of logic here, and you want to use it here, you can do two things. You can make a generic library or generic class out of it and use it from two places. Or you can take this and you press Ctrl-C or Command-C and you paste it here. Who prefers who prefers copy-pasting? I have some friends in the audience. We'll get back to that later. So obviously this is a trivial example. And there are lots of different degrees of coupling. Usually you want to have low coupling, so it's easy to change. But every generic solution with shared code introduces at least some coupling. So we've probably all read the books by Robert C. Martin and learned about clean code, right? So clean code explains the concept of dry. Don't repeat yourself. So ask for yourself, if you are strictly applying dry, you don't repeat yourself anywhere, does this increase coupling in your system? Yes, dry increases coupling. So I'm not saying that dry is bad. I'm saying that you shouldn't follow it in a vacuum. So if you kill a piece of duplication, you're applying dry, then you are taking responsibility for predicting that those pieces of code will change together from now on. So basically, you're looking at the future and say, these will never individually change. If they're likely to change independently, then you've even caused confusion and extra work for little benefit. So a trick of knowing when to apply dry is if you can find a really good name for the component you're extracting. If you can give this a really good name, then it may be a good idea. So, well, we've all learned about dry, and that is bad. But what if I tell you, and my friends in this part of the audience will love this, and you will hate me for this. What if I tell you that duplicated code doesn't hurt until you need to change it? So, if I have two pieces of code, I have a piece of code here, I need it there. I copy-paste it, it works. What's the problem? Well, it's a bit itchy, right, that it's there in two places, but it's not hurting anyone. It's super cheap to copy-paste it. It's in those places, working fine. Why should you then, before knowing what the future developments are, refactor this to a reuse component? You could see this as a form of premature optimization, right? You don't know if they're going to develop themselves identically in the future. They may, but they may not. And even if you've duplicated code and you change something here, and now you need to change it there as well, right? How much work is this? Well, there's regex search replace in IDEs. There's tools like Open Rewrite that can automate those things. So it may be a little more work fixing something here and there. And there's also like the cognitive load of knowing that you need to fix it here and there, because maybe you only fix it here and then the problem is still there. But extracting it to a generic component and reusing that may be, in the long run, even more work if you don't need to change this code that much. So we often say that software design is about making things future-proof. So how many of you think that if we develop software, we should develop the software in such a way that we are prepared for future changes? Hopefully everybody agrees, right? I'm not going to become mad at you, but if we develop software and we don't think it can be changed in the future, then, well, it's going to be useless pretty soon. So design should be structured to accommodate change. But if we're asking about how to make things future-proof, isn't that as simple as asking, can we predict the future? Last time I checked, we couldn't do this. So how do you make code easily changeable? Well, I think we can be prepared for any future change by making code really simple. Because if it's really simple, there's no unnecessary abstractions, no unnecessary complexity, then it's easy to change the code in the future, and it will be sort of future-proof. So also here, think about risk management and about the significance of a decision is measured by the cost of change. So if it's something that's easy to revert, go ahead. If it's something that will take weeks to revert, okay, maybe think a little bit longer. And I think Victor Rentea made a great point this morning when he was talking about API design. So he showed this slide, and he said that if you build future-proof APIs, you lose clarity. So if there's an emails field that only has one, and you add an array there because maybe you have more emails in the future, well, you don't know you really need this. If you have a phone number and you add like a type, so you may be able to add more phone numbers in the future. If you have like metadata, you can add random fields. Well, those APIs become less clear to understand and less clear to evolve. And I have another example to explain this. So this is a little story about a project I did a while ago. And this was a project for the government. So it was a public tender where the organization that needs software writes a really detailed document about what they need, and every company can say, I want to build this and it will cost this, and then usually the cheapest wins, and then the project gets in trouble. That's how these things usually go. So the company where I worked had won this project, and on my first day of the project, I went to sit at my desk, installed my local environment, and opened the home screen of the application, and it took like 6 seconds to load. And I was like, is there a lot of data in this database? And my colleague said, no, maybe I don't know, a couple of hundred rows. So why does it take six seconds to load? Is there something wrong? No, I don't think so. So what's going on? And I was looking in the logs, and there was a database query was going off. And I said, oh, I don't know a little thing about database queries, so can you maybe get me this query so I can have a look at it? He said, sure, how do you want it? I said, can you print it for me? Print the database query so I can have a look like what the problem is. So he smiles at me and he walks away. And he comes back like, I don't know, 15 minutes later or something, with a stack of paper this big. And it was like 6,000 lines of SQL that was going off there. So I said, why didn't you tell me before? And he said, well, you didn't ask me. So why was this query so long? That's, in the end, the question we want to know for a trivial screen. So the reason was that the government that wanted this project, they had hired 2 architects. And those architects, they had the experience from previous projects that software was difficult to change. So they wanted to protect the customer, the government. They wanted to protect the customer from getting a system that is hard to change. So as a result, they designed a system that was super flexible. So it was so flexible, you could configure everything. So in the admin interface, you could add fields to every screen, you could add values to every drop-down, everything was configurable. And to make it even worse, they designed the system so it should be in 2 parts, and those systems should synchronize with each other, synchronize data. So this system became so complex because of all the extra fields. You need to do, like, I don't know, 10 queries to fetch data for one simple page. So as a result, this software became super difficult to understand and to develop and to maintain. And in the end, the project almost failed. And we got to convince the client that we should throw away most of the complex stuff we had and build something really simple. Luckily, this helped. But if I look back, it was some kind of like a self-fulfilling prophecy. The architects, they felt that software was hard to change. So they designed a really, well, let's say, flexible system that made the system super complex. And as a result, it became hard to change. So this is what their result was there. So write simple software is what we can learn here. So the late Stefan Tilkov said it, I think, pretty nicely. He said that highly specific code is often preferable to sophisticated configuration. So I was going to tell you about generic versus specific design. When are we finally going to talk about this? Now. So pay attention. So about those levels, where can you apply generic versus specific solutions? Well, obviously on a code and a class level, reusing a method or reusing a class. You can think about having manually written code versus generated code. If you have duplicated generated code, is this maybe a different problem from having manually code that you've copy-pasted? I don't care too much about code I generate, because you regenerate it anyway when you want to change something. So using a library or not. So using a library or building something yourself, extracting generic logic to a reusable library. You can make decisions there. On a data level, so for example, reusable data types or something. So I once worked for a company that was building software for insurers, and there was a standard for exchanging data between insurance companies. And it was called GIM, which stands for Generic Interface Manager. So it was an interface, that's all right. But as soon as something contains generic or manager, start asking questions, right? So this was a standard. And the nice thing about standards is that everybody uses the same data format in this case. So you could see it kind of like as an open API description on how to exchange data between insurers. And this was maintained by the CV, the Standardization Institute for Insurers. So what every now and then would happen is that you need to exchange a piece of data, and there was no field for this in the standard. So then you would call the CV, some guy would pick up, and I said, yeah, I need to exchange this piece of data with an insurer, and I can't find where it is in the data catalog. And I said, oh, okay, I'll get back to you. And then a day later he gets back and says, yeah, I have the answer for you. So, okay, what's the answer? Yeah, the answer is there's no field in the data catalog to exchange this piece of data. Okay, so what now? Yeah, so it is a valid field to exchange, I feel. So I'm going to make a design for it, and I'm going to propose it for the new version of the standard. And then people are going to vote on this, whether they think it's a good idea. And then we're going to send it out to the world, and then all insurers are going to update their software to use a new standard. And then you can use a new field. So that sounds awesome. So how long do you think this will take? Yeah, about 1 to 3 years probably until it's everywhere. So then we talked to the insurer and we misused some field and put our data in there so that at least we could exchange it, because we couldn't wait that long. So this is, I think, the problem a little bit with standardizing too much. So you can also talk about generic for specific on a service level. For example, how do you handle security in microservices? Do you build this in every service, or do you use a library? Or do you maybe use, I don't know, a proxy or a sidecar to handle security? And also on an organization level. So when do you do something project-specific, or when do you build a generic solution that multiple teams will use? And this usually is the hardest thing, because all those things before, they're just about technology. But if you are reusing something in multiple teams, now people are involved, which makes it a bit more difficult. So the questions we're going to discuss, they live on all those levels, and they have different implications on different levels. So how do you decide to go for a specific or a generic solution? Before we can finally answer this question, we first need to look at one more concept, and this concept is abstractions. So when you're making something generic, you're making an abstraction. So you're making a generic solution for one or more cases of a problem. So what an abstraction does, it generalizes over a problem and over a solution, and then find basically common behavior and hiding implementation details. So a type of abstraction you probably all know is database access, right? So JPA or Hibernate or Spring Data. The problem space is I need database access via queries and a database driver. And the solution space is all databases that are supported by JPA. So the nice thing is that as a developer, you don't need to worry about specifics in Postgres or MySQL or Oracle or DB2 or whatever. You can reuse the database access stuff because it's abstracted. It's a nice generic solution. But also a JDBC driver itself in the Java world is an example of an abstraction. But as we see later, abstractions also have a cost. So let's talk about a couple of tools to help you decide between generic and specific solutions. The first one is Yagni. How many people have you heard about Yagni? Almost, well, half of you. You ain't gonna need it yet. So whenever somebody proposes something, shall we solve this in this way? You can ask them, do we really need this now? And the nice thing is you can emphasize a different word in this sentence, and it means something different. So you can say, do we really need this now? Do we really need this now? Do we really need this now? Well, you catch my drift, right? Keep asking this question until you're sure that there's something you need now. If not, probably better to postpone it when you really need it. Another tool is using the 5 Ws. So whenever somebody wants something, you can use the 5 Ws to figure out why they want it. So the first W is easy. That's why. Somebody wants something, I want to abstract something, refactor something. Okay, first W is why. Then a second one, and this is an important one because this is often forgotten, this is why. So I want this because I want to reuse. Okay, why do you want to reuse? Third one is easy, that's also why. And you keep asking why until somebody either has no answers anymore, or you completely understand why they want something. And if the end result is because I feel like it, or I don't know, some reason that doesn't really check out, well, then you have a discussion. You can think about the time and effort to solve something generic versus something specific. If I have a piece of code, I copy-paste it, it takes, I don't know, 1 second, depending on how fast I can copy-paste. If you need to extract a class or a library or a service, it may take more time. But if I need it, I don't know, in 1,000 spots, then probably making a generic solution is a better solution. Also realize the myth of the first time right. So how many of you are regularly in a situation where you see a problem, you come up with a solution, you start typing, and within a couple of minutes it's done and it turns out exactly as you envisioned? How many of you regularly have this? No one. So how many times does it usually take you? Like, I don't know, 2, 3 times? 4, 5 times to try before it's right? Right? So usually, if you see a problem in its first occurrence, you don't really understand it well enough to make a reusable solution for this. Also think about complexity and scope. If it's well-defined, has a limited scope, you can just solve the problem at hand. If it's super complex, there's a wide range of potential scenarios, maybe you could go generic. The rule of 3, we will talk about it on the next slide. And maybe think about future needs and evolution. Well, we already know we can't predict the future. But if you already know there's going to be some future needs that you're already aware of, you can incorporate this into your design. So Gunnar, a friend of mine, said it, I think, quite nice. He said that a fair share of software design is professional procrastination. Basically waiting as long as possible for you to make a decision. In order to avoid locking yourself into a corner or to committing on the wrong abstraction too early on. So the rule of 3, it's quite easy. When you're reusing code, you copy it once, and you don't start abstracting to something generic until the 3rd time. So this helps you avoid writing the wrong exception. And it's also easier to have 2 pieces of duplicated code and then refactor it to the right abstraction instead of making a wrong solution first and then trying to make it fit to your 2nd or your 3rd problem. So this is often also called 3 strikes and you refactor. So the first time you see a problem, just build it. Don't genericize it at all. Solve the problem in front of you. You ain't going to need it yet. So in the 2nd case, copy it. Maybe redesign, maybe extract some common behavior while you change it. Not until you have the 3rd case where you need this. Take a look at the lessons you learned from the first 2 passes. Design something generic that will make it easy to add your 3rd case. So now you change your first 2 cases. With the knowledge, there will be a 3rd case. So once you've refactored those, it will be super easy to connect the 3rd one. So another tool you can use to help you decide is strategic design. And this is a concept from domain-driven design. And it's a tool to help decide something generic or specific. But more about building it yourself or reusing something or maybe buying something. So in strategic design, you look at a couple of subdomains from the perspective of custom software development. So you're writing software yourself. So your core domain is something what makes your organization special and different from your competitors. You cannot do business without being super good in your core domain. So you probably want to build this yourself and have the best developers you have work on this. You may have a supporting subdomain, something that's necessary for the organization to succeed, but it's not part of your core domain. It is not generic either, because there may still be some level of specialization. So you may be able to start with something existing and tweak it to your own needs. So not really custom development, but also not taking something generic from the shelf. And then a generic subdomain is something that does not have anything special to your organization, but is still needed for your overall solution to work. For example, usually stuff regarding money, like invoicing or payments. Unless you're a payment provider, you're probably not going to build a payment system yourself, but you can use, I don't know, Stripe or any banking system or whatever. And then there's Conway's Law, and this is mostly for the organizational part. So Melvin Conway said, and I think he was right, that organizations design systems that mirror their communication structure. And what we can learn from here is that we probably should not design and force a solution that goes against the organization structure. So if there are 3 teams who do not want to work together at all, and you have a problem, and you design in such a way that there's one generic component that those 3 teams should use, well, they're probably going to fight or not going to use it. So be careful to go for a generic solution when teams don't want to work together. So a little story here, basically the impact on Conway's Law of choosing generic versus specific. So I used to work for an educational publisher, and they had 3 business units for 3 different school types. And they basically were 3 different companies inside the company. And at one point, they all somewhat together asked the IT department, can you build me an e-learning system? And the IT department knew that they all wanted pretty much the same system. But the IT department also knew that it probably wasn't going to work to build one generic system. Because if 3 different business units ask you to build something, and then you build one system, and it goes down because, I don't know, business unit A screws something up, and then you need to explain to business unit B, yeah, the stuff you gave me money for to build, it's now not working because business unit A screwed up. Or you get discussions on priority or features. Why cannot I have this feature now? Well, because we're now building a feature for the other business unit. I don't care about the other business unit, I'm giving you money, right? So the result there was 3 different e-learning applications with some reused code. So as an IT department, we could see These things are generic. We can reuse those of those solutions, but one generic solution definitely was not going to work. So going generic may save you time in the long run, but at which price? There's another rule of 3. That's building reusable components is about 3 times as difficult as building something that you build once. So also 3 times as expensive. So the price you pay obviously is coupling. And the coupling is both on a code level, so coupling between pieces of code, but also on a people and team level. And then you get some communication and planning overhead. If you have a generic component that 2 teams uses, and there's a breaking change in there, and team A needs this change. We want to do it next sprint. They go to team B. We're going to make a breaking change. Can you plan this for your next sprint to upgrade to do this breaking change as well? No. This is not important for us, but it is important for us. So now you need to sync your backlogs to make sure that they all move in the same way. Obviously, there are solutions with versioning here, but don't underestimate the overhead you get from syncing backlogs of teams to each other because they reuse something. So what if you get something wrong? Well, let's go back to abstractions and think about the cost of abstractions. There are no zero-cost abstractions, so every abstraction has some cost. So the efficiency gains of going generic are typically clear, but how about onboarding new people in something complex and generic? How about readability for a generic solution? If it's in one place, you can just read the code top to bottom. If it goes here and then it calls to some library that you need to find the source and then figure out which code flow is executed there, it becomes more difficult to read. Coupling, talked about this a lot already. So if you're writing bad abstractions, then you're writing unnecessary reusable code, which is a shame. You're introducing unnecessary coupling. So you're making the code more complex than necessary. But you're writing the code only once, but you're maintaining it a lot of times. So maintaining bad abstractions, they may be hard to see, they may be hard to understand, they may be hard to extend. So there may be a lot of extra costs for more complex solutions than actually necessary, because they're more difficult to understand. So why should you go generic? Well, first start with bad reasons. We've always done it like this. Well, and has this helped? We don't really know. We don't want to depend on libraries. Well, do you really think that you as an organization are better at building something than, I don't know, an open source team has been doing for 5 or 10 years? Probably not. We need to be future-proof. Well, we already know we cannot predict the future because the product owner wants it. Well, the product owner can tell everything they want about functionality, about priorities, about usability, but not about our technical solutions. And then my favorite one, because the architect wants it. Well, when this happens, you can call my friend Benny the seagull. Here he is. So I like to call this seagull architecture. So I think roughly translated, arquitectura de gaviota, right? So if you should see this as this, the development team is walking in the city or at the beach, let's say at the beach. And then the architect flies high over, it looks down at the development team. It comes down as a seagull, it shouts, ah! It drops her shit on the team and then flies back up again. This is seagull architecture. So the problem here is that the shit is only going down. It's going down from the architect to the team. But it's not going back up again. So as an architect, you should be actively seeking feedback from teams. Does the solution that I throw down on you actually help you solve those problems? So valid reasons can be the rule of 3 checks out. Or you're pretty sure you're going to need it almost everywhere. Security, metrics, logging, those kind of things. A library that a lot of teams will use for any of those things. And this is an interesting one. Complex logic or skills that only a couple of people have. So you can also use a generic solution to encapsulate a piece of complex logic. Let's say super complex, well, don't build it yourself, but cryptography or any of those things. If you want to make sure that only a couple of people can work on this, then make a generic solution that's owned by one team and only this team can edit stuff here. And when the gains are bigger than the cost. But that's often difficult to see. So think back about those layers in hierarchical decomposition of a system. Code versus component versus service. Are those the same on every level? Are you going to think the same about reusing a piece of code or reusing a service in an organization? Usually the risk of getting it wrong is higher when the level is higher. If you make a reusable service and now 10 teams need to use this, and it turns out it wasn't a good idea, the problem is bigger than when it's only in one class. But also don't confuse generification with standardization. So making a generic solution means sharing code. But you can standardize without sharing code. If you standardize on doing REST in your organization, you standardize on doing OAuth, you can still standardize on those protocols without reusing code there. So a short intermission on why specific is often faster. We're going to look at a little hobby of mine, which is code challenges. So the first one is code golf. With code golf, you get a challenge. You need to write a piece of code in the smallest amount of characters of code possible. So you get all kind of nice tricks, like you don't say return true, you say return 3 is larger than 2, because 3 larger than 2 is only 3 characters, and true is 4 characters, right? So the challenge here was optimizing the shortest solution possible for verifying a bank account number or something. So, I was one of the first to solve this challenge because I logged the bank account numbers that were sent to this application, and I found out that I could just say if the last number is odd, return true, otherwise return false, because there were only like 5 bank account numbers. And then the person organizing this found out, and then he put like 1 million bank account numbers in the challenge, and it didn't work anymore. But I still got quite well in the results because I did this. So this is a client server application in less than 100 characters. Basically what I did is say, okay, go to this URL. Well, this doesn't really work. Go to this URL, add the bank account number to the URL, open a stream and read 1 byte. If it says something, if it says 1, return true, otherwise return false. And then on my server, I could build the application as many of characters as code as possible, right? So basically I cheated, they found it out, but still got an honorable mention. So another one is Advent of Code. How many of you have ever participated in Advent of Code? It's like a programming contest. That's an Advent calendar. You get 25 of those until Christmas. So this one was a challenge where you get some text input. Here you get these stacks. So you get 3 stacks of crates, and then some operations. So move 1 from 2 to 1. Basically means you need to move the D to stack 1 here on the left. And then the actual puzzle input is obviously a bit more complex. You get loads of different stacks, and then it says move 1 from 8 to 1. So you're basically going to move the B here from stack 8 to stack 1. So when I see this, my mind goes, matrices, right? I need to build a generic solution that can read all this and then implement the matrix, and then I can maybe able to use this for the future. So my code looks something like this. You don't need to read all this code. You are reading the code, right? Don't do it, it will give you headaches. But then I saw my colleague's implementation, and it looked like this. So basically, he hard-coded all the stacks, and there's even like some indentation errors in here, and he used this as input for the challenge. So who do you think was faster? I spent half an hour building, I don't know, the matrix implementation. This took him 1 minute. So this is, I think, a good example why specific solutions are typically a lot faster for the first implementation. But it can also be the other way around. So to give a counterexample, think about how you handle exceptions in an application. So if it's in a Java or Spring application, you can write an exception handler for every screen, or you can do something like this. So this is aspect-oriented programming. It's an advice, something that wraps around every controller you have. If an error is thrown, it goes through this method. So now you need to solve this problem only in one place. But this works because exception handling is a fairly, let's say, generic problem in applications. So a final example is about, well, reuse of code for a website that we made at OpenValue. So we have a couple of websites, like a site, a blog, trainings, but my favorite one is this one. This is a website that shows our cats. So this shows all the cats of people that work at OpenValue. So the first thing that we did to get this out of the door is to build just static HTML, right? Simplest thing that could work. So then, once we needed to make some updates every now and then, it became a pain to edit the static HTML. So we built something a bit more generic, like you have a JSON definition of the cats and the images, and then we generate this site. So now we were ready to move to release our next website, which is a website that displays all the dogs we have in the company. But because of the rule of 3, we will first copy this. So we copy the cat website to the dog website, edit it there, and not until the, I don't know, maybe the third animal website we get, we will make a generic solution, like, I don't know, a pet website. So this is our dog website for the dog people. Do we have dog people in here? Cat people? So the people didn't raise their hands. What's your favorite pet? Snake. A snake website. So the URL of this website is openvalue.dog. I'm going to leave it as an exercise for you what the URL is of our cat website. So let's see. Yeah, we have some time to look at this. So sharing code in an organization is hard to share code efficiently at scale. So this means that you have multiple modules that share code. There's multiple team members that work on it. There's a high rate of change, and you want little to no loss of productivity. So it's easy to share code. It's difficult to share code effectively. So challenges you have is refactoring. You rename a field. It has impact on 5 other projects. How do you tell them this? Versioning. Do you let everyone upgrade at their own pace of the generic components, or do you force people to upgrade to the latest and greatest every time? Reviewing. So if you need to change something, you need to update dependent projects as well. Change that may become super big. And also maybe builds and code base size, right? So let me move on to one slide further. So some considerations on sharing code is in a larger organization is discovery. So how will people know what generic components exist? Do you have like a wiki or an API repository or something like Backstage? How do you know which generic solutions you can use within your company? How do you distribute them? So are you distributing binaries or source dependencies? Binaries you can version. Source dependency may be a bit more difficult to use versioning there. How do you import those generic things? Do you use well-defined APIs or the YOLO methodology, whatever you like? How do you handle versioning and upgrades and lifecycle management? If a new version of a generic component comes out, how long do people have to upgrade to the latest version? When are you going to retire the previous version? And who maintains those generic things? Often the answer is no one, and whoever wants to will update those things. It can help having a specific team that handles the generic libraries in your company. So a possible approach here is to use some sort of an inner source culture. So it's basically open source, but inside of a company. You have some repositories that have maintainers that are responsible for those repositories, but everyone can contribute by making issues, by doing pull requests, whatever. So, time is almost up, so it's time to summarize. Should you solve stuff in a generic or a specific way? Well, you can consider, you ain't gonna need it yet. The 5 W's, don't forget number 2. The cost of generic solutions, and basically the cost of abstractions. The scope and the level. Reusing something on a class level is usually a bit less risky than reusing stuff on an organization level. Commerce law, so don't design systems that go against the communication structure of your organization. And the impact on your organization in general. So, should you go generic or specific? I'd say that overall, it should be based on a careful analysis of the problem and the potential future needs and evolution. So the honest answer, I think, is it depends. It's always a trade-off, right? But I do hope that you now have a couple of practical pointers to apply next time that you face a decision. So in the end, it's not necessarily about getting it right from the start, but it's about getting it right in the end. And the reason is this. I think this is a quote from also Robert C. Martin. A program that works perfectly now, but is impossible to change, it will become useless over time. But a program that does not work, but is easy to change, it will become and remain useful continuously. So if I need to give you one piece of advice that I hope will stick, it's simple advice. Write simple code. If you have questions for me, feel free to approach me. I'll be here today and tomorrow. I hope you can use this newfound knowledge to go kick some ass in making design decisions. And there's two more things I want to ask you. First is, the next speaker in this room is the amazing Brian Vermeer. He's over there, and he will show you how attackers exploit common Java security mistakes and how you can stop them. So don't go anywhere. And second, please scan this QR code to rate this session. Be honest, but also be generous. Thanks a lot for your time. See you around.